You now have information on the design fire size, the mass flow rate of smoke, the average temperature rise within the smoke layer, and the actual temperature of the smoke layer. With this and some few other pieces of essential information, you can now calculate the requirements for smoke exhaust, whether that be by natural ventilation or by powered fans. Before we calculate the smoke exhaust requirements, we should say a few words about acceptable smoke temperatures. One of the requirements of a smoke control system of this type is that the smoke rises to the ceiling to form a distinct smoke layer under that ceiling. The smoke will only do this if it is sufficiently buoyant. In other words, if it's sufficiently hot. Therefore, there is a minimum temperature rise below which it is considered that smoke will have insufficient buoyancy to form the required smoke layer at ceiling level. And this minimum temperature rise is 20 Kelvin or 20 degrees C. Smoke will rise at temperature rise figures of less than this, but it must be remembered that the smoke might have to travel some distance beneath the roof before it's removed via a ventilator, and it will cool further as it travels towards the ventilator, perhaps dipping below a level of buoyancy that will keep it at ceiling level. If a smoke reservoir was small and there was little expectation for smoke cooling once it had entered the layer, then consideration might be given to lowering the lowest acceptable theta value to a little below 20 Kelvin. Where mechanical extraction is used, the limit of 20 Kelvin might also be considered a little higher than necessary. There are no quantified models to assist in the prediction of what a real safe lower limit might be. Computational fluid dynamics, or CFD, can be used to assess if smoke will remain at ceiling level, but there have been a number of cases recently where fire engineers have made erroneous assumptions when carrying out this analysis. For example, errors in the assumed rate at which heat is lost to the ceiling or walls, or inappropriate cell sizes have led to incorrect conclusions about the behaviour of the smoke. Such assumptions should either be very accurate or should err on the side of safety. Also, provisions will be required within the CFD model to ensure that an accurate assessment can be made of the behaviour of the smoke and of the outside air at all open ventilators. As well as a lower acceptable temperature rise limit, there is a higher acceptable temperature rise limit. The upper limit depends upon the construction of the building and on whether or not people will be required to pass beneath the smoke layer when making their escape. If people will have to pass beneath the smoke layer, then the smoke layer temperature should be no more than 200 degrees C. This is often represented by a theta temperature rise of 185 Kelvin or 185 degrees C. And this would be the case where ambient air temperature is taken to be 15 degrees C. At 200 degrees C, people beneath the smoke start to feel pain where the heat radiates down onto them. If people do not have to pass beneath the smoke layer, then the limitation on the acceptable upper temperature level should be expressed in relationship with the fire resilience of the structural parts of the building that it collects in. If the building is constructed with steel beams that sit within the smoke layer, and those beams cannot safely withstand temperatures above 400 degrees C, say, then it is likely to be one of the jobs of the smoke control system to keep the temperature of the smoke layer down below the level where the damage would start to occur to the structural members of the building. The ambient temperature is often attributed a value from a small range of possible values, usually between 15 degrees C and 20 degrees C. It used to be common to use 15 degrees C, but it's probably more common nowadays to use 20 degrees C. In terms of Kelvin, that's 288 Kelvin, which is equal to 15 degrees C, or 293 Kelvin, which is equal to 20 degrees C.